Our next presentation title is Effect of Superabsorbent Polymer on 3D Printing Characteristics as Rheology-Modified Agent. And I would like to introduce our speaker today. Our speaker is Yu-cun Gu. Um, Dr. Yu-cun Gu received his master's degree in Shenzhen University in 2019 and his PhD in civil engineering from Missouri University of Science and Technology. He is serving as the postdoctoral researcher for Dr. Kamal Khayat Group. His research interests include the development of sustainable hydraulic binders, toxic substances, solidification, stabilization, high performance cement. He has participated into multiple projects as the main investigator, including state DOT projects in Missouri and Illinois Tollway. Um, Dr. Gu is a peer reviewer of Cement and Concrete Composites, Journal of Cleaner Production, and Journal of Materials in Civil Engineering, Construction and Building Materials. So I'm very pleased to welcome Dr. Yu-cun Gu.
Good afternoon, everyone. I am Yu-cun Gu, and first of all, I would like to thank for NES and ACI to provide this opportunity for me to give this presentation. Today, I'm going to bring a topic about the effect of superabsorbent polymers on 3D printing characteristics as rheology-modified agent. So before I go further to this topic, I would like to introduce what is superabsorbent polymer and why we use it in cement-based materials. Superabsorbent polymer is a type of polymer can absorb water by 100 and even 1,000 times of its weight. And for example, 1 gram of super SAP can absorb water up to 100 grams. Typically, it is used for water absorbent pads, water jar, and water retention for supplying water to plant, and even it is used for artificial snow. And it has multiple usage. And why we use it in concrete? Because it can use in concrete as internal curing agent. It absorbs moisture inside concrete when it is in fresh state and release the water gradually to sustain the relative humidity inside the concrete when it gets hardened. In this way, it can significantly reduce the shrinkage of the concrete, and we all know the shrinkage of concrete is a very big problem. And it induces cracking and thence reduce the strength and durability of the concrete. And this photo shows a project we use SAP in pavement concrete, and it do its good job for reducing the shrinkage. And so, in the past 5 years, the researchers start using SAP in 3D printing concrete. And why we use it? Because for the 3D concrete printing, it has high volume of binder. It does not require it does not has the formwork, and also it has high surface volume ratio of filament. And so the drying and cracking in 3D concrete printing is really a big problem, and it can lead to reduced transport properties and durability. So the researchers start using SAP in 3D concrete printing to solve this problem. And I'm giving an example here. So this study was conducted by Dr. Molik, and so we can see this. Let me use the pointer. Okay. Now we can see the left figure. The orange line is represent a mixture made with SAP, and black marker represent the reference mixture. And we can see that by adding the SAP, the shrinkage can be significantly reduced for 3D concrete printing. That's why we want to use it in 3D concrete printing. But as it brings some advantage on reducing shrinkage, it also introduced some very big problem in 3D concrete, printing concrete. We all know that we need the printing concrete to be flowable when when we pump it and when we extrude it. But when after extruding the concrete, we need it to become hardened as soon as possible. But as SAP, as I mentioned, SAP absorb and dissolve water during the mixing, and it definitely will affect the workability and rheological properties of concrete. And so this became a big problem, and also become a challenge. but a challenge usually means opportunity. Another idea in the recent 2 years or 3 years is that can we use it? Can we use the SAP, this characteristic, to control the rheology on 3D concrete printing? And then I start my research in the last 2 or 3 years. We choose couple type of SAP. Today, I want to introduce two normal traditional type of SAP. SAP1 is the acrylic polymer with average particle size of 850 micrometer, and it represents the black line in this figure. And this figure, it means the absorption rate of SAP when it's saturated in the filtrate pore solution. So initially, we can see that in 1 minute it absorbs 10 gram water, and then gradually absorb water up to 1 hour, and then dissolve the water slowly. And for the SAP2, it is acrylic polymer with average particle size of 500 micrometer. It represents the yellow one. So it absorbs water very quickly in the first 3 minutes. But after that, it dissolves water also very rapidly, and in around 1 hour, 90% of water has been gone. So these two different type of SAP is a bit two different absorption and dissorption capacities. And then we choose 3 different reference mixture, and these reference mixture are made without SAP. So the reason why we choose these three reference mixture, because this mixture show different disotropy. We determine the disotropy using 2 parameters. We measure the static yield jet at 5, 15, and 30 minutes, and then we determine the first parameter called flock value is the first the increase in yield jet after 5 minutes of rest. In this figure is this value. You see the flock, this value, and the ADs indicate the rate of structuration during the linear evolution. In our case, is the structuration rate during 5 to 30 minutes. It means this. And then our reference mixture, we developed this in the past, and this mixture all of this mixture are replaced by 50% of cement. And the first mixture is a bit medium flock but high ADs. And the second mixture, we here call it binder 2. It has very high flock value and a medium ADs. And the third mixture, binder 3, has both low value of flock and ADs. And we choose this measure because we want to investigate the effect of SAP on the mixture with different disotropy. Yeah, and then here show the mixture proportion. We have done many mixture. So the first category is reference, and the second category is a mixture made with SAP but without additional water. So we can see here the water binder ratio is 0.3. So in the label of the mixture, or label 0.3, and the SAP with 50% water is 0.325 water binder ratio, and the SAP with 100% water is 0.35. We use the additional water only for SAP1, because SAP1 gradually absorb water and do not dissolve water. And we use different superpreciser content to maintain the initial slump flow. So all the mixture have the same slump flow after around 190. Before and after 25 joule, we use the Minicom's flow table test to measure the workability. And then we measure the basic rheological properties, the dynamic stress and the plastic viscosity. And based on the literature review, we come up with printable region of the dynamic yield stress and plastic viscosity, and all of our mixture can fall in this printable region. It means that at least for the first layer, we can print this mixture. And then I would like to go to the effect of SAP on the structural buildup, the thesotropy. So this mixture is a by the one, the reference mixture. And when we add the SAP here without the additional water, we can see that SAP1 result in 25% higher flock and also 180% higher ADIS. But SAP2 here, it reduced the flock from 800 to 600 Pascal. So it has two different effects on the structural buildup. And then this is the effect of SAP on binder 2. And binder 2 has high flock and medium ADIS. And so for this in this case, the SAP1 also, without increasing water, binder ratio also led to 40% higher flock value. It's very high, 1,800 Pascal is really high, and also it result in higher ADIS. But also SAP reduced the flock by around 25%. And why we measure these rheological properties and thesotropy? Because these properties are closely related to the printability of concrete. And then I would like to correlate these properties to the actual print quality. So we used a Ganges 3D concrete printer. The nodal diameter is 30 millimeter, and it has printing speeds. We set up the printing speed as 50 millimeter per second. It's pretty fast, and the filament size, the print filament size, around the width is around 48 millimeter, and the height is 50 millimeter. And we do not stagger time between layers. And the vertical buildable rate is pretty high too. It's around 138 millimeter per minute. So it's around 8 meter per hour. And then we print the mixture until it got failure. And we just print a single layer as this figure show here. And with around 330 millimeter long. And I will show two videos. The first video is when plastic collapse happened and the bottom layer deformed. So the failure happened, we record the maximum buildable height. And the second one is elastic buckling. Because we print a single layer, so when elastic buckling happens, it means it has very good thesotropy property. And in this case, the bottom layer still can sustain its shape. And then, first we go to investigate the effect of SAP on the edgeability. We evaluate the edgeability based on the surface quality. And this is the binder 2 with the very high flock one. So we can see the reference mixture made without SAP. There are many tears and open void on the surface, even though these tears and open void are small, not very big. But as we add SAP2, the ones can dissolve water rapidly. Also, the one reduce the flock value. We got a beautiful surface, just with very few tears on the upper layers. So, and also another case is binder 1. Binder 1 has a medium flock value, and so the binder 1 has a relatively smooth surface. But and we continue to add the SAP2, it has a perfect surface without tears, as the photos show. And in this case, we can make a conclusion that the use of SAP2 can improve the edgeability of mixture with high or medium thesotropy. But how about the effect of SAP1? The one keep absorbing water gradually. And so the figure A is still the reference mixture. And then when we add SAP, it increase the flock and also significantly increase the ADIS from 60 Pascal per minute to 160 Pascal per minute. Yes, we still got a very good surface quality, just with a little bit more tears, but the width of the filament become narrower as we keep printing. And to this layer, we cannot print anymore because the width is just like 25 millimeter. So it affects the etchability. But as we increase the water by the ratio to 0.35, it has the same quality of the reference mixture. And this is the effect of SAP1 on the binder 2. For this one, because it increased the flock value to a very high level, we can see significant tears on the surface, even though the tears happen completely on the cross section. It's not, we cannot continuously print the structure. And also, when we increase the water binder ratio, it becomes better. It becomes similar, has a similar property of the reference mixture. So we make a conclusion that increasing water binder ratio is needed when you use SAP1 in order to ensure a good etchability. And after that, we have a table here. We summarize all the surface quality mixture. We measure the maximum tear width. We measure the maximum tear length. And also, we record when the blockage happens. And so for the binder 1 and binder 2, I already give a detailed discussion. But how about the binder 3? And here, let's see, I highlight the 3 mixture made with SAP for the binder 3. And basically, there are no tears happen on the surface because binder 3 already have very low dissolvability. And let's see why. But does that mean all SAP can be used in binder 3? The answer is no. So the binder 3 mixture had very low dissolvability. So the failure happened very early at around 11 layers. And when we use SAP2 in this mixture, it further reduced the dissolvability. And the plastic collapse happened even more earlier. It means that SAP2 is not recommended for mixture with low dissolvability. But when we use the SAP1, it can significantly increase the dissolvability value and then improve the resistance against the plastic collapse. And finally, based on this mixture and the mixture we investigated in the past, we come up with this etchability window. So the green window, the green region means the mixture can be printed with relatively good surface quality. Also, with the plastic collapse do not happen. And when we use SAP2, it goes to this area. When we use SAP1, it goes to this area. So when we consider using SAP in 3D concrete printing, we definitely need to consider the properties, the biological properties of the reference mixture. And in this way, we judge which SAP can be suitable for this mixture. And then let's go to the section how SAP affect the maximum buildable height. As I also mentioned, the plastic collapse, when we use SAP, increase the plastic collapse. But how about its effect on elastic buckling? And you must know that when we use the SAP for the mixture with medium and high dissolvability, whatever the SAP, S1 SAP with actual water or S2 SAP without actual water led to a 5% to 20% reduction in maximum buildable height when the elastic buckling happened. So what's the reason? We use the penetration resistance measurement to investigate this effect. This is very simple test. We use the penetration resistance. Normally, we use the penetration resistance measurement according to ASTM C403 to measure the setting time of concrete. And then in our case, we measure the evolution of the penetration resistance since it is in very early age. And then we develop some process parameter to indicate the capacity of the mixture against the elastic buckling. So we develop a processing parameter called the time to achieve a certain value of penetration resistance. For example, time 150 defined as the duration to reach 150 kilopascal, and then normally a lower value having a higher buildable height. And in this case, we also measure the T250 and T350, and we got these relationships. The buildable height is correlated with this processing parameter, and our result indicated that use of either S1 SAP and the SAP and also the SAP2 can lead to a longer T 250, and so that's why it reduces the buildable height when the elastic buckling happens. It reduces the stiffness evolution of the cement-based materials. So as it reduces the buildable height, another question is that why we use SAP? Because buildability is also another important factor, and that's why, as I mentioned, the answer is it improve the attributability, and attributability is also very important, as I described earlier. Improve the surface quality of the filaments, and also it will improve the interlayer bond between layers, and then it will result in a better strength. So now I'm going to the strength section. We measure the compressed strength of a mixture which the sample cast in the mold, and also we cut the Prince filament as shown in figure B here, and we measure the compressed strength of the sample in two orientation. For example, the orientation 1 is like this. The bond layer is here, and the orientation 2 is like this. The bond layer is horizontal. And then we come out. So first, this slide shows the result of the cast sample, and when we add SAP, without additional water, it can significantly increase, not very significantly actually, it increase the strength around 10%, because this is because it's because of its internal curing effect. As we increase the water by the ratio, the water by the ratio become higher. It got a little bit higher, a little bit reduction. And overall, the compressed strength of the mixture either made without SAP and with SAP are very similar. But how about the compressed strength of the print specimen? We compare the compressed strength between the cast and print specimen. We calculate reduction as a percentage here, and we can see from this figure, the reduction of the compressed strength is pretty higher for the reference mixture, and the blue column mean the orientation 1, the orange color mean the orientation 2, and so here we can see for the orientation 2, it come up to around 58% reduction of compressive strength for the binder 1, and this is really a lot. It means that our strength of the specimen is around 6,000 psi, but we can only got 3,000 psi for the print sample, and so why it happened? Because we got a very poor bond strength and bond performance, and also we got a back surface quality. As we add the SAP2 to the mixture, we can show these two compared to the reference. The reduction of the compressed strength between the cast and print specimens decrease a lot. This is why another advantage we use SAP2. It improves the surface quality. It also improves the bond performance, and then it increased the compressive strength of the print filament. And This is a figure show the relation of lithotripsy on the reduction in 28-day compressive strength. As I mentioned earlier, SAP2 reduce the flock value, the SAP1 increase the flock value. And we found that there is a strong relationship between the flock value and also the reduction in 28-day compressive strength. That's why the SAP 2 can improve the compressive strength. It reduce the flock, improve the surface quality, improve the bond strength. And so overall, we have these key findings based on our research. The acrylic SAP1, the acrylic SAP is a one we call SAP2 here, can be used to improve the isostripability. And the use of the acrylic co-acrylamic SAP can be used for the mixture made with low lithotripsy to improve the resistance against plastic lapse. Additional water is recommended for this type of SAP if we use in the mixture made with high lithotripsy. And then the compressive strength is also dependent on flock value. But I want to clarify this, why it is related to the flock value in our case, because we print the structure within the 30 minutes after mixing. And the flock value also is measured during this region. So it's more closely related to this flock value. In some cases, if you print a large application, it may finish within the 30 minutes. And then in this way, maybe it is also related to other factors such as the ADs and the environment and the surrounding environment. And then overall, the acrylic SAP can be used as a rheology-modified agent to reduce the flock, consequently leading to improvement in bond performance. We published this result in these references, so you can go for further details in these two references. Thanks. Questions?
Great. Thank you so much, Yu-cun, for your presentation. It looks like there are many research is going on, use of SAP and the bond behavior. So with this, we can go with the questions. Do you mind just sharing the presentation, or I can share the screen? Because now I can see GoToWebinar. Okay, yeah, that's better. Thank you. So one of the question we have is how thixotropy affects the interlay bond of 3D 3DCP, and also does SAP also affects the structure build-up rate?
Okay. We developed the lithotripsy into two parameters in our case. The flock represent the initial 5 minutes, and the ADs represent a later stage during 5 minutes to 30 minutes. I do think it really closely related to the printing process, your setups of printing. In some papers, it also indicates the bond performance is closely related to the ADs. In our case, it is more closely related to the flock value because, as I mentioned, we print the structure in a we complete the printing process very quickly after the mixing. And if you go to the larger application, it might be more closely related to the ADs. That's how the lithotripsy. Also, if you got a high lithotripsy, normally it will reduce the bond performance. So it does not say, because we hope that the 3D concrete printing to have very good buildability, but it does not mean we need to have a higher and higher lithotripsy. We need to have a good lithotripsy to ensure it has good buildability and also has good bond performance. That's how the lithotripsy affect the bond performance. Yeah.
Okay, great. Thank you so much. So also, like on the similar lines, the question is, will the built-up rate affect the interlay bond? So will that affect the bond behavior?
Yes, it can affect the bond performance. Yes, but it depends on your printing setup. Yes.
Okay.
Yeah. So I will give an example. I read a paper. It set up the get time as 5 minutes, 5 minute gap time. And it means that it print the first bottom layer, and after 5 minutes, it start printing the second layer. And after 5 minutes, it start printing the third layer. And in this case, the AD, it is more closely related to ADs, but also it is more closely related to the surrounding environment. So your temperature, your wind speeds on the top of the surface, and and the surface moisture of the filament. These all factors together affect the bond performance. In our case, we do not set up the gap times because we found that we have a good buildability even though we do not have gap time, and we print the structure, finish printing the structure in a short time, so it is closely it is related to the flock, but we do not find it is closely related to the environment and also the ADs. Yeah.
Okay, great. Thank you. Our next question is how to determine the additional water of SAP in 3D printing concrete. I think you did cover, but if you could just elaborate a little bit more on that.
Okay. So first of all, in our case, the water by the ratio is 0.3. When we use the 0.3 water by the ratio, it has both, problem of autogenic shrinkage and drying shrinkage. If we increase a little bit more additional water, it increases the drying shrinkage, but it reduces the autogenic shrinkage. In this case, we measure the total shrinkage. We combine these two shrinkage, and then how to determine the additional water? The first, you need to consider the strength and the shrinkage. So you need you investigate the effect of SAP on your mixture. On mixture, different mixture have different properties, and you come up with the most good ultimate content of additional water. That's why I choose 3 additional water for the SAP one. But in the meantime, when we use it in 3D concrete printing, the effect of additional water on the physiotropy and rheological property, we also need to consider this. For example, SAP1, when we use it in the mixture made with high physiotropy, if we do not add additional water, we cannot make it. And and also, if we use other mixture made with different water by the ratio, it has different results. For example, if we use in very high water by the ratio, 0.4, 0.45, you may do not need to add the additional water. You also have very high fluidity, and the main problem is the drying shrinkage. And if you use it in UHPC with very low water by the ratio, 0.2, 0.18, yes, additional water is needed.
Great. Thank you. Yeah, I have one more question, but before that, just a reminder for all the audience that if you have any questions, please type it in the question box. So our next question is, what are the factors affecting the absorption kinetics of SAP?
So the absorption dissolption of SAP is mainly affected by its own material properties, such as the type and size. I just give an example of 2 types of SAP here. The acrylate one usually has rapid dissolption and absorption. Another one, acrylamic co-acrylate polymer, has a gradual absorption and then gradual dissolption of water. And another factor is that it's surrounding moisture environment. We use it in cement, so you use different binders. So when we use different binder, it will slightly affect its absorption, dissolption, and also slightly affect its maximum absorption rate. And even though you use different mixture, and so the problem is that when we use SAP, we need to measure its absorption pattern, right? And but your mixture get changed, we need to remeasure this one. So this factor all affect the absorption and dissolption of SAP.
Okay, great. Thank you. So I don't see any more questions, but we can give like a couple of minutes. If there are any questions, please write it in the question box.
Well, I wrote a question, Aparna.
Okay.
Did you see it?
Yeah, no, I didn't see the question. Please go ahead and ask the question.
Okay, I would like just to since you mentioned UHPC, how would the fibers come into play when it comes to the material properties in your research?
The fibers. You mean the fibers?
Yeah. UHPC does have steel fibers.
Okay. Yeah. We have some research companies and also ongoing research about the UHPC with different fibers. So majorly we use steel fiber. We investigate the length of fiber. So the length is the most important things we use. For example, for our printer, we use 30 millimeter nozzle and 40 millimeter nozzle. It just can accommodate the 6 millimeter steel fiber. If we go to the 12, 13 millimeter fiber, it will depend on the rheological properties of the mixture. If it has a low dynamic yield stress, low plastic viscosity, yes, it still works. But if it has high dynamic yield stress, and we cannot print it. And then, so it also related to your printer, the nozzle size, and also setups. We use the screw type printer. And sometimes you may use the RAM and also those printer, with pressure that may, improve this problem. It may improve this problem. So it also related to the content. For UHPC, for example, we use 1% replacement of the fiber by volume. It works good, but if we go to 2%, 3%, yeah, that is also it depends on the rheological properties of the mixture. Yeah.
Great. Thank you. Do you have any more questions, Dr. Akno?
No, actually, he provided great answer. I really entertained the answer. That's very explaining and eye-opening. So thank you so much for the answer.
Thanks.
Thank you.
Appreciate it.
Yeah, so thank you so much, Yu-cun, for this presentation. So with this, we're almost at the end of our virtual seminar. We are going to end a little early, but I think.
Yeah. Thanks, Aparna. Thanks for ACI to organize this event for us.